be able to present about this work that I'm very excited about here. And the development is actually being extended to two more formal subjects in physics. One is to develop a systematic relation between lattice QFT and continuum QFT, which certainly fits the title of this conference perfectly. And this is seen as a route to make sense of a continuum QFT, at least one promising potential approach, right? And we'll see what developments will happen there in relation to the lattice-Yang-Mills-Instanton problem. Another direction is that we all know category theory has been appearing in physics for like 2 or 3 decades. Mostly category theory has been applied around the IR limit, where the theory becomes a TQFT or CFT, and it's mostly talking about symmetry, anomaly, or just kinematics in general, and it's been mostly working with discrete degrees of freedom. And now we want to see what lessons we can learn from those stuff, but apply them to more generic QFT at generic energy scales with generic dynamics, and usually with continuous degrees of freedom in more realistic models. So what we'll primarily work on is to solve the lattice-Yang-Mills-Instanton problem in a natural manner, but we'll see that these 3 directions in physics really are coming together, which make me feel very excited. So the problem we are dealing with is that the topological operators will in generally be spoiled when we try to put continuous value degrees of freedom onto the lattice in the traditional way. Let's look at the simplest example of this kind, whose solution is actually known, but we'll talk about solution later. Now let's just look at the problem. Let's consider S1 non-Niskanen model in condensed matter called XY model, where we have an S1 degree of freedom living on each vertex, right? And let's consider for simplicity a one-dimensional lattice. Then we obviously feel that these 2 configurations should have winding numbers 1 and 0 respectively, right? Otherwise we are lying to ourselves. But obviously these 2 configurations on the lattice can be continuously deformed to each other, right? You just focus on one single spin, gradually rotate the direction of the spin to whatever value you want, and you do that one by one, right? Then you can continuously deform any lattice configuration to any other one. But then the topological number would jump at some point, right? No matter how you do it in detail. So more formally, this is because the configuration space in the traditional lattice model has S1 to the power of number of vertices. And this is a connected configuration space. So when you want to map to different topological classes, which is discrete, no matter how you do it in detail, you certainly are going to encounter some discontinuity, right? So this is the simplest example of this kind of problem. And the problem we are facing is a more involved version of this, but along the same line. So let's look at SUN Yang-Mills theory, where we have this SUN Wilson line degree of freedom on each lattice link. And we focus on the holonomy around each plaquette denoted as DG. And in the continuum, we know the instanton has an expression like trace F wedge F, the instanton density. And the integral of the density over a 4-dimensional manifold with suitable boundary conditions is an integer. And we feel that if the DG on the lattice is sufficiently close to identity, then F is roughly speaking log of DG, right? But when we do a lattice sampling, they're in a large system size, one cannot guarantee that DG is close to identity everywhere, right? And in that case, the logarithm is not a single value function. Actually, for the same reason as before, no matter how we do it in detail, taking log or whatever, because the configuration space on the lattice is connected, because it's just SUN to the power of links, right? This is a connected space. When you want to map to different topological classes, there must be some discontinuity somewhere. And all the current approaches on this problem, like Lucius admissibility restriction, or the flow method introduced just now, or the fermion index method, all have discontinuity, like there's this jump or bifurcation of flow somewhere. And if you're a TQFT person, you certainly will recognize that when you apply the group cohomology method to, for example, SUN, you'll encounter cochains that suffer from the same kind of discontinuity. So this really hints that they are closely related problems. And now there is a long list of examples of continuous degrees of freedom on, with topological configurations, and we want to realize them on the lattice. And it turns out that the simplest cases, the pi 1 and pi 2 physics, has been solved decades ago. But then the things we're more interested in now, like, for example, the S3 non-infinite model, which is the pion non-infinite model, we want to focus on, for example, the skyrmion, which is the baryon, or the SUN gauge theory, where we want to talk about non-abelian Chen-Simons and Instanton and Young monopole. These are pi 3 physics, and of course there are other more general physics. And why those solutions are known for decades, but these are not? Well, certainly people tried very hard, but it turns out that the solution to these more general problems have the same intuition as the previous known examples, but there is some mathematical gap that requires more systematic picture, and that is what we are going to develop in this talk. So the talk is organized as the following. First, I'll introduce why the idea behind this solution is rooted in the V-line model. And then I'll talk about how this idea from the V-line model is actually can be developed into a mathematically natural framework. But when you want to do it for more general examples, cat theory becomes necessary. So now, not everybody endorses category theory yet, but everybody likes cat. So I think it's, and also category theory is usually abbreviated as cat. So I think it's helpful for various reasons. And I will, after introducing this mathematically natural and fascinating framework, I will actually show that you can actually write down a model from this seemingly very abstract mathematics. The model is practically implementable, and moreover, it's physically intuitive. It's so intuitive that when you look at the final model, it seems like some steps of it even appear as sort of unintelligent. But what category theory does is to tell you that those steps are not unintelligent. Those are the more flexible mathematics that is needed. Okay, so let's start with the idea rooted in V-line model. So let's come back to this example where we said, okay, the winding number, no matter how we define it, seems to jump somewhere when we implement the lattice model in a traditional way. And this has been solved by the V-line model decades ago. And it was actually first developed by Berezynski for obvious reason, because he was about to discover the BKT transition. So we'll see that being able to implement topological operators on the lattice in a natural manner actually led to important discoveries in physics historically. So the philosophy we want to introduce is this. Now let's consider the lattice as being embedded in the continuum. Then the lattice link is like a path in the continuum, right? Then in the continuum, we will want to ask, okay, we know that the two angles, theta, are here and here, but how does it interpolate along the path, right? It's a very natural question to ask. Then, of course, there are different ways of interpolation, right? You can interpolate short way or the longer way, or you can wind a few times before you reach your endpoint, right? So in the continuum, the interpolation gamma would be this integral, which is a real number instead of U1, right? Because there's a distance of interpolation. That means on the lattice, if we want to capture this interpolation information, we should literally introduce a real number on each link. The L labels the link here. So gamma L is a real number on the lattice link, whose U1 part is subjected to this constraint, because right, it should capture a difference of the angles. But the integer part of the real number is not fixed. And that ambiguity should be summed over with suitable weights, right? The intuition is that the shorter interpolation should have higher probability, right? It's all very intuitive. And what is good about this is that because gamma is introduced with this physical motivation, the winding number obviously is just the sum over gamma on all the links on the loop, right? And then you can see that the d theta part on in gamma cancels out, and the remaining thing is manifestly an integer. So the winding number is manifestly well-defined. And in terms of the partition function, more explicitly, the traditional XY model has a periodic weight in d theta, because theta is by definition a periodic thing, right? So it has to be periodic. And what the V-line model does is it introduces this integer, which is the integer part of gamma on each link, And as we said, the weight should be weighted about the interpolation distance, right? And the intuition, as we just said, is that shorter interpolation should have higher weight. Longer interpolation should have lower weight. So the weight W1 will look like this, where 1 means the link is on a link, and link is one-dimensional. Okay, so W1 gamma should look like this to satisfy our physical intuition. And how does the V-line model recover the XY model? Well, you just sum out M on each link. Then that will shift the center of the gamma, and then it will generate a periodic function in d theta. So you can recover the XY model arbitrarily well. Okay? Well, it's unimportant to recover it exactly because that has a lot of UV details. But at least you should recover the qualitative features, in particular the periodicity. So it seems like after summing out M, we just recover XY model, we have done nothing. But the important thing is we can do things before we sum out M, right? Because before we sum out M, we can define the winding number unambiguously. So that's why we say the V-line model is refining the XY model, right? Because we can do more things before you sum out M. And in 2 dimensions, let me go to this slide. In 2 dimensions or above, we can actually do more. Why? Well, let's now consider winding number around a single plaquette. What is that? That's just a vortex, right? Vortex is a winding number around a single plaquette, and it's the lattice curl of gamma, which is again an integer. And now in a 2D or higher dimensional model, we can introduce a weight on each plaquette, which is the vortex fugacity. We can penalize vorticity however we want. Or even in the extreme case, we can forbid vorticities entirely by a Lagrange multiplier. And this phi is U1 because the vorticity is an integer. And this will manifest due d-2 form U1 global symmetry, and it's mixed anomaly with a 0 form U1 of the XY model. And we are not going into those details, but those are very manifest, very easy to work out. And the history of the V-line model is Berezynski invented it on the way of discovering BKT transition. So it really shows that defining topological operators is very useful. And then V-line invented it for numerical purposes. And I want to emphasize that including this vortex fugacity on the lattice actually facilitates renormalization. Because you can imagine that when you do coarse graining, those effects are going to be generated anyways. So you want to include it in the action just to keep track of the flow of it. And technically, you can also think of it as effectively generating some semantic improvement. This also allows an explicit derivation of the boson-vortex duality. And in the limit where the vortices are forbidden, the boson-vortex duality becomes the T-duality, and both orders are here. And I also want to mention that we can also apply the V-line model, not to non-infinite model, but to gauge theory, where the S1 degree of freedom on each vertex now become a U1 gauge field on each link, and then the real valued interpolation gamma on the link now become a real gauge flux F on the plaquette. You ask why in the U1 gauge theory the flux is real valued. Well, now we can look at this picture. We imagine a Wilson loop starting at the lower left vertex and gradually grow in its size until it matches the size of the plaquette. Then the holonomy of the Wilson loop should interpolate from identity to some U1 value, right? So again, we have this interpolation length, which should be described by a real number. And then the winding number in 1D just now becomes a Dirac quantized flux in 2D, and the vorticity in 2D or higher now becomes a monopole in 3D or higher. And this procedure, very intuitively, of putting every degree of freedom in one-dimensional higher lattice cell actually correspond to de-looping in category theory. And all this villainized gauge theory was developed also soon after the original V-line model. And I just want to advertise that the U1 V-line gauge theory has seen a revival in the recent years in the purview of symmetries and anomalies. Chen and Christoph worked on it, mostly focusing on the abelian instanton context. And myself focus on condensed matter context of fractional quantum Hall, first with double Yuan Chen-Simons, and later, more excitingly, with chiral Yuan Chen-Simons Maxwell, which is closely related to Theo's talk on Monday. And the Maxwell is needed there for some fundamental reason, which I will not explain. And we can reproduce the chiral edge modes, where each color represents a chiral edge mode on one side of the sample. And we can get the chiral gravitational anomaly and the ground state degeneracy with the R torsion spitting out, but equal to 1 on 3 torus, and so on, all the interesting things. And also, the Yuan V-line model has been applied to the fraction model, fracton models in this paper by Shu Heng, Hota, and collaborators. Okay, so this is so much about the V-line model. We already see that it led to the important discovery of BKT, and it's useful for many other things. And what we'll do in the following is conceptually the same, retrieving the interpolation information effectively. And primarily, our purpose was to naturally capture the topology. But what we get as a bonus is that it also facilitates the renormalization for very intuitive reasons. So now let's distill the philosophy from the V-line model and see how it can develop into a mathematically natural framework and why categories become necessary. So the philosophy is that when we want to assign topological numbers to traditional field configurations, there will be discontinuity. And what V-line model does is that new degrees of freedom are introduced, some of which are discrete, such that they are coupled with a traditional degree of freedom for the purpose of capturing the interpolation information that would have been there if we were really in the continuum, right? And the discrete new degrees of freedom will determine the topological numbers, and because they have joint coupling with the traditional fields. So the traditional field only probabilistically determine the topological numbers. And in the known examples, including the V-line model that we said just now, these new and traditional degrees of freedom actually form principal bundles. Right, so now we motivated the V-line model from this geometrically intuitive picture. And algebraically, what happens is we are realizing S1 by its universal cover R and gauging a Z gauge redundancy. And by doing that, for some mathematical theorem in homotopy theory, the pi1 of S1, which is the topological stuff we're interested in, is naturally captured into the pi0 of Z. And that's why the V-line model works. Another kind of known models since the 80s is the spin-on decomposition of S2 non-insigma model, where you represent the S2 degree of freedom as SU2 gauging a U1 gauge field, and in condensed matter that's recognized as a Berry connection, and then you further villainize the U1 gauge field. In doing that, the pi2 of S2 is captures the pi1 of U1, captures the pi0 of Z. And geometrically, the interpolation picture is like you have two spin directions on neighboring vertices, and then the red curve is like some arbitrary interpolation. But that has too much infinite dimensional detail, right? It can wiggle around like crazy. You just represent it by some SU2 rotational curve. As long as the black curve and the red curve bound zero area, which is zero Berry phase, you ignore that difference. So that's the sort of intuition behind it. So this is the principal bundle story behind the V-line model and the spin-on decomposition. But now that you have organized this known example in such a fashion, it seems obvious that if we want to work with a pi non-insigma model or SUN gauge theory to capture the pi theory of things, we just extend the ladder by one more step and we are all set, right? And furthermore, we can even recognize that U1 has good physical meaning. In non-insigma model, it's the 2D WZW curving, and in 3D, in Yang-Mills, it's the 3D Chen-Simons 3 form. It seems all good. Except these question marks cannot be filled out. Why? The reason is also pretty simple. In non-insigma model, the double question mark would occur on a link, and in Yang-Mills theory, it will occur on a plaquette. So we want this degree of freedom to be able to compose, right? Because they are link variable or plaquette variables. And traditionally, when we think of things composing, we think of groups. And moreover, we want them to be finite dimensional, because these are lattice degrees of freedom. We want to be able to sample things. But the simple fact is all finite dimensional Lie groups have trivial pi2, so they are not going to fulfill this requirement. Actually, by a little bit more mathematics, you can show that not only would groups not work, any fiber bundle, so these like stairs are actually fiber bundles, any fiber bundle would not fulfill the goal. Okay? So just for this simple reason, once we organize things in this way, we see that to carry out this philosophy of V-line model, which is physically very intuitive, but to more general problems, we need some more general rules of the game, which is that of the higher categories. And actually, this philosophy of the V-line model that we just schematically picture has a very natural correspondence in category theory, known as Anna-Functor, which people developed to deal with various problems in topology, in logic, and so on. And what is the feature of category theory that is there, but not in group theory? Okay, so category theory really is very much like a board game, like Settle of Catan or something. Okay, when we first learned mathematics in elementary school or kindergarten, we say, okay, 3 plus 2 equal to 5, or some matrix multiplies some matrix equal to something. And yesterday in Shu Heng's colloquium, he told us a serious physicist should not write arrows, but should write equal signs because it's unambiguous. But like in playing this game, what is the canal composed with a row equal to? It's not equal to anything, right? But we can still play this game, and the computer can also play this game. So this is the feature of category theory that we are going to use. And as a CAT person, CAT theory practitioner, I'd say the equal sign is actually ambiguous and sometimes does not exist, but the arrow is actually more well-defined. Okay, so that is the reason that category theory is useful. Without introducing category theory, because obviously it's impossible in this talk, I just want to advertise 2 excitements. The first is that using this philosophy behind the V-line model, Wilson's goal of using lattice QFT as the foundation of continuum QFT actually has a natural confluence with the mathematician's goal of using category theory as the foundation of homotopy theory. The idea is that if we consider field configuration in the continuum, what is it? It's just a map from the space-time manifold to the target manifold, right? And what do we want on the lattice? Traditionally, we are just sampling some discrete points in the continuum. Then, of course, we are losing a lot of information. But in the continuum, once we know how each point map, we can also know how each path map, because the path is made of points. We will also know how paths between paths, which are surfaces, map, right? Because they are all made of points. So in the continuum, doing this gives us nothing new. But on the lattice, if you include lattice paths, you retrieve more information. And lattice plaquettes, even more information. And when you do all the d-dimensional lattice cells, the lattice fills up the entire continuum. You retrieve all the continuum information. But the continuum information has too much unimportant UV details, right? Reflected in the fact that the path space in target manifold is in general infinite dimensional, and also the surfaces and so on. So now, what we want is to truncate away those unimportant details, but keep the important stuff. And I would say my main contribution is that this vague physical problem organized in such a way becomes a well-posted mathematical problem. We want to find a finite dimensional category that is nonetheless equivalent up to what we want to this infinite dimensional category. And we will use that finite dimensional category as the lattice degree of freedom on the vertices, links, plaquettes, and so on. Okay, this is the trade-off between the seemingly simple but infinite dimensional continuum stuff and the seemingly complicated but finite dimensional lattice stuff. And actually, this idea extracted from the V-line model is pretty much how the mathematicians develop higher homotopy theory itself. So this, I think, made me feel this must be the natural solution to the problem. And for Yang-Mills theory, there's a similar story, with Wilson's theory being some sort of lowest order approximation. And as we have seen in the Yuan example, the non-linear model is related to the Yang-Mills theory roughly by putting every degree in one higher dimensional cell. And in category theory, that's called delooping. But for a general problem, including our Yang-Mills problem, the delooping procedure actually involves solving a Yang-Basset equation in order to define Yang-Mills theory. You will not imagine these 2 works of Yang are related to one another, but they really are. And magically, in the physical intuitive construction, which I'll briefly introduce momentarily, the Yang-Basset equation is automatically solved. We don't need to do anything. And I don't understand why that is the case, and that's something I want to understand better. But just by advertising this, you can sort of feel that the idea that we extracted from the V-line model can be developed into a very fascinating, very natural mathematical framework that can do a lot of things naturally. And the second excitement I want to share is that while the purpose is to correctly handle continuous degrees of freedom, when we apply the same stuff to discrete degree of freedom, we automatically recover the TQFT models, like the Digraph-Witten, Toureff-Vito model, without manifestly introducing the fancy language of tensor fusion category. So this hints that there might be a more unifying cat theory language that is applicable for both TQFT and generic QFT. While I'm not able to explain that in detail, here I just want to emphasize one very important difference between finite discrete gauge field and continuous gauge field. That is, for discrete gauge field, we can safely consider just flat gauge configuration, right? So, and usually we consider Digraph-Witten twist, which is realized by this group cohomology, H3BG U1. And the BG there actually means the gauge field is flat on the lattice, okay? For Lie group gauge field in Yang-Mills theory, there's no reason that you demand the gauge field to be flat, right? In condensed matter terms, it does not have an energy gap in the UV. And actually, if you demand that, the partition function will in general be divergent for some reason. So what we're really looking at is generic gauge field configurations. However, your Yang-Mills section is able to distinguish how flat or how non-flat your gauge field is, right? It's not agnostic about that. It knows that more or less probabilistically. So you are led to consider relative cohomology between a generic gauge field versus a flat gauge field. And here we will look at H5 with Z coefficient, which counts the Young monopole. And this is realized by the Anna Funter thing, which is behind what is behind the V-line model that I just explained. And this Anna Funter realization of cohomology is a generalization of the group cohomology by taking into account continuity and group equivariance, and it's a very general language that can go beyond groups and abelian coefficients. So this, at the beginning, I said this lattice instanton problem is related to the group cohomology problem for continuous Lie groups, and this is sort of the explanation to that. Okay, so much about the fancy mathematics, and in the remaining few minutes, I just want to show that a model can actually be written down, and it's physically very intuitive. It can be understood without any background in category theory. Okay. So the idea is, okay, what we have is one-dimensional traditional Wilson line degree of freedom, and what we want is some 4D stuff. So our philosophy is we should fill in some 2D and 3D stuff. Moreover, we know that the 3D stuff is going to be a Chen-Simons space. Why? Because in the continuum, the incident density is D of the Chen-Simons. So on the lattice, you should do this V-line thing so that the sum of that is not going to be 0, but some integer. So this is a 3D version of V-line. And this idea has actually appeared in a paper of Seiberg's in the 1980s. However, the model of Seiberg still suffers from the discontinuity that we motivated at the beginning. And what we crucially do is that we have this 2D stuff bridging the 1D and 3D stuff in a manner that is continuous and captures the topology correctly. So the model looks like this, where you have some traditional degree of freedom on the links. And then you have some plaquette degrees of freedom, which cannot be formulated in terms of groups or fiber bundles, but nonetheless they can be made sense of. And Tin suggests that they might be related to central vortices. And in 3D, we have a U1 dynamical phase, which is the Chen-Simons. And in 4D, we have this villainizing integer. So this is the lattice model. Let me just briefly introduce what this non-group thing is. So the traditional Wilson theory considered holonomy around the plaquette DG, and the weight should only depend on eigenvalue because of gauge invariance. And the weight should look like this, right? The further from the identity, the smaller the weight is. Now, when we think about refining this, it's like we want to think about how the gauge field interpolates into the inside of the plaquette. So we again consider Wilson loop that is growing larger and larger in size. So we will consider two ways of interpolation. One is to interpolate from the identity to DG along the geodesic. The other is to interpolate from 1 to -1, which is the central vortex, a thin central vortex, and then from -1 to dg along the geodesic. Why we want to consider at least 2 ways of interpolation? Because this way of interpolation, the geodesic interpolation, will become more and more ambiguous when dg approaches -1, right? Because the direction will become more and more ambiguous. Similarly, when dg approaches +1, it will become more and more ambiguous. So minimally, we need to consider 2 ways of interpolation. So the Paquet degree of freedom is refined to this set of things with these constraints, where these constraints to avoid ambiguities. Okay, and we can note that although we have 2 labels M, but they are in no sense a Z2 group. So this is not a group, and moreover, Y is not a fiber bundle over SU2 because we have these restrictions. And in terms of the weight, this is the traditional weight, and now we are decomposing the traditional weight into a sum of 2 possibilities. And when each possibility becomes ambiguous, the weight just goes to 0 smoothly for intuitive reasons. All right. So this is what we do on the plaquette. And then on the cube, I don't have much time, but let's just go over quickly. Now that we have sampled the gauge field on the links and we sample the possibilities of interpolating in the plaquette, we want to consider interpolation into cubes. And different interpolations into the cubes will give different Chen-Simons spaces, right? But now we're going to ignore the details of the interpolation, only focus on the Chen-Simons space. That's why we have a dynamical degree of freedom, U1 on the cube. And then these are some technical steps, but what we are going to do is we are going to construct some suitable saddle point for the Chen-Simons space fluctuation and control its fluctuation. And one very important aspect is that when some interpolation becomes ambiguous, the fluctuation becomes arbitrary. So that really means there's no preferred interpolation. So that will ensure we capture the topology correctly. And finally, on the hypercube, we villainize the Chen-Simons U1 and get the Instanton density. And that's the 4D model. And if we focus on 3D, we can just ignore all the hypercube stuff, and we can introduce such a phase. And because the Chen-Simons is manifestly U1, the K has to be an integer. And this is the Chen-Simons Yang-Mills theory, where the Yang-Mills must be there for fundamental reason, just like the U1 case. And in 5D, we can define the Yang monopole, and this might be helpful for understanding what is whether a 5D Yang-Mills theory has an interacting fixed point or not. Okay, because the Yang monopole is considered, whether you have Yang monopole is considered probably important there. So that is roughly speaking how the model is written. And since I don't have much time left, but those are the outlook. The first section is the near-term things that we're going to do. And in particular, numerical implementation is certainly the first thing we want to do. And I myself failed at the stage of installing Python on my laptop. So I'm getting some people to help me. And the second segment is some midterm things to do, which requires some development in mathematics. And the last segment, I think, is some long-term ambitious prospect, which nonetheless, I think we really should seriously think about. Because now we have this framework that is bringing lattice QFT closer to our desired continuum QFT. And I'll stop there. Thank you very much.
Thanks a lot. Very interesting talk. Yes, Sal is.
Yeah, thanks for the great talk.
Thank you.
So the target space of your fields, you always had it as some geometric realization of some higher category.
Yes.
Is this higher category always a higher groupoid?
Yes, because at least in the physical model we consider path. The path can go backwards. So it's a higher groupoid, but it's in general not a strict one. It's like, but it's nonetheless invertible in some suitable sense. Just like how the non-invertible symmetries are not invertible in the strict sense, but you always are able to find something that composes with whatever you have, and you have a possibility of getting the identity. So similar to the non-invertible symmetry, but it's invertible in a generalized sense, yes.
So is it always, as a space, homotopy equivalent to looking at like some truncated Postnikov tower of the target?
Yes, but we want to choose a suitable implementation of that, so it's finite dimensional and has some other nice properties.
Okay.
But it's essentially doing that. Yes.
Okay, thank you so much.
Yes.
So I don't know whether I understood everything completely, but is there a notion of locality also for this?
Yes, it's manifestly local because our weight is on each plaquette, each cube, each hypercube, and all the degrees of freedom also all live there. And we can define the local Instanton density on each hypercube.
Okay, and one would also be able to check something like reflection positivity.
Yes.
Yeah.
For the abelian case, like the abelian Chen-Simons, we can check the reflection positivity. And for this refined model, I think the reflection positivity is also true this is part of the definition actually. Like when you reverse the orientation, how would this Chen-Simon saddle should just change its sign and so on. But yeah, I want to have a more rigorous expression for that, but I think it's reflection positive. Yeah. In the abelian case, it's manifest. Yeah.
So it looked a little bit like you wrote an expression for the path integral weight of e to the I theta q. Is that right?
E to the I theta q.
Yeah, you wrote the partition function.
Yeah.
Okay. Is it possible to use your technology to get the topological charge itself, not its exponential?
Yeah. So yeah, here this is the Instanton density, which is the valencized real number of the Chen-Simons plus an integer, and the sum of that over the entire 4D spacetime is the Instanton number.
I see. Thank you.
So you go back to your last slide.
The last slide. Yes.
Do I understand the last remark as this might be an appropriate tool to win the Clay Millennium Prize?
Well, certainly in any case, we are very far from there. But my gut feeling is that if we are moving there, maybe very slowly, something like this should be included, right? Because the topological stuff do appear in the renormalization process. You should be able to take them into account naturally, just like what happened in the V-line model. So I would believe it should be part of that. Yeah, but the technical analysis aspect of that is very difficult. Yeah. What I heard from Arthur Jaffe is that Balaban once lost his draft papers, and then after he's not going back to the same problem anymore. Just because he lost the draft papers.
So I have a question, but first I need to make a comment to arrive to the question. So
yes.
I have experience in computing the topological charge and the topological associability and higher moments in two-dimensional CPN models on the lattice,
right,
where I can use two different definitions of the geometric topological charge and one non-geometric. And one of the geometric one is very similar to the one that you showed at the beginning, so that the remainder modulo 2 pi of the difference of the phases, okay?
Right.
So what happens in practice is that even if you use a geometric charge which is exactly integer, even on a gauge field of the lattice, you still need to do some gradient flow or cooling to define, for instance, the topological associability. Because even if the charge is integer, since it lives on a single lattice spacing, it has crazy large lattice artifacts. So if you want to take the continuum limit and reproduce the analytic calculation at large n, you have to do the flow.
Because that will fluctuate a lot.
Exactly, because every little UV fluctuations, it interpolated to an Instanton, but it's not true because just a UV artifact. So my question is, it seems to me that you are still working with a definition which lives on the scale of one lattice spacing. So my fear is that if I could implement your proposal on a lattice calculation, I would find crazy large lattice artifacts. So I wanted you to make a comment on this.
My feeling is that probably you shouldn't need to cool stuff, because certainly in the V-line model, you never cool anything and it works perfectly fine. Yes, I think it's more about the definition of topological susceptibility rather than the definition of the model. That's what I would feel like the case, especially based on our experience of the V-line action. For example, there's a very simple proof that in 1D, the 1D lattice, the V-line model is the perfect action. So this is like, it's capturing the renormalization very nicely. So I feel like maybe our notion of topological susceptibility is the thing that we want to clarify rather than the model. Like,
so your answer is that since it's the perfect action, there will be very small lattice artifacts. If I understand correctly.
Whether it's perfect action depends on the detail, but I would say this is a good ansatz for the perfect action because all the new degrees of freedom on the new ways have good physical meanings. Yes, rather than just writing down hundreds of complicated terms, this is a better ansatz towards the direction of perfect action. That's what I would say. Yes. That's actually, by the way, that's actually Will's suggestion when I visited MIT last year, and I really appreciate him. Yes.
Does your, let's call it generalized Yang-Mills theory on the lattice, does it have a manifest one-form symmetry, and do you know how to couple it?
It has. Yes, and moreover, well, I just mentioned this plaquette thing, and if you couple like this plaquette degree of freedom, if you couple the two forms ZN background gauge field, it will shuffle the probability of these labels, right? That's why Tim made this suggestion that it should be closely related to the notion of center vortex, although center vortex is not well defined. And then related to that, I want to bring up this point in the concluding remark where I really want to explore. That is, the ideas from topological order was helpful for me to develop this Instanton thing in the Yang-Mills. Then it seems natural that ideas from symmetry enriched topological order is helpful for the central vortex problem. Yeah. I think that's close related to your question. Yes.
Can you generalize your SU2 to SU3?
Yes, I have a backup slide for that. Okay. So this is the eigenvalues of SU2, right? So we are considering two ways of interpolation. One is from the identity to wherever we want, and the other is go to minus identity and back to there. For SU3, we consider three possible ways of interpolation, each going through a center vortex, including trivial center vortex. Yeah. So that's why this might be closely related to central vortex, although I don't know how to make that precise at this point. Yes.
So the question I was going to ask is, does this line of thinking have any phenomenological consequences, or maybe phrased differently, does it suggest different observables that one should look at that one wouldn't have considered previously?
Well, so at least for the traditional problems that we are interested in, even if you don't care about instanton, I believe this will facilitate renormalization, just like how the Villain model worked. And if you look at instanton, I would say at least now you have a more unambiguous definition of the instanton. So looking at instanton-related things, I think you have a more unambiguous definition rather than, for example, cooling, you need to decide how long you cool and so on, right? And there are more general observables that you can look at, including some very formal mathematical problem that is related to finding the Hamiltonian formalism. Actually, to find a Hamiltonian formulation of this, or finding more general observables in this formalism, is equivalent to solving some mathematical problem, which I don't think exists in the literature. Maybe I didn't search hard enough, but my impression is there is some exciting math behind that. Yeah. Maybe I'm thinking of it at a too high, like too abstract level, but that's what will come to my mind. Yeah.
Yeah, this is just a comment, because I remember that in the old times there was a proposal by 't Hooft to do precisely an interpolation in plaquettes, cubes, and etc. Such that, he would use the boundary and then interpolate to the interior in such a way that, for instance, to define the fermions would live on the continuum manifold. That didn't go very far off, but well, it's just a comment that maybe it's interesting to look back into that.
Yeah, for fermions, I don't know for now. So Lucier also did this interpolation into
the geometrical charge, yes, but this was something different.
Right. Okay, so maybe I'd be happy to learn about that works of Hooft. Okay. Yeah, and I would say the distinction between this and Lucier's thing is Lucier fixed the interpolation into the plaquette and the cube. I am sampling different possible interpolations. That's the key difference. Yeah. So I don't know, but thank you for this. Yes.
John, maybe the last.
Is your Chern-Simons theory subdivision invariant?
Is what?
Is your Chern-Simons theory subdivision invariant?
No. Actually, even the abelian one is not, because because it just cannot be. Let's consider chiral abelian one. If it's subdivision invariant, then you can coarse grain until the lattice has only one cell. Then there is impossible to have a chiral edge mode, gapless chiral edge mode, right? So there's some fundamental reason that chiral theory is not exactly topological. It has some topological limit, but only as IR limit, but it's only as an IR limit. Yeah, on the lattice, we can see this at a more technical level, which I also have a backup slides, but I don't know if I should show it now. Unless you really want to, yeah.
Okay, well, I think we're a little over time and dinner is waiting for us. So it's been a very interesting session. Let's thank Jing Yuan again.
Thank you.